And welcome to the first lesson of our last unit, our last chapter for the year, in which we're going to bring a lot of the concepts together that we've seen before and start to talk about acids and bases. And in today's lesson, we're basically going to talk about some specific properties of acids and bases, and we're going to look at the first of our two models for how acids and bases work. And tomorrow we're going to come back and see our second model. So acids, as you may know, are corrosive to skin. So this is a chemical burn. If you get acids on your skin, that's going to burn. And they're also corrosive to certain metals. And this is a reaction we've seen before. This reaction, hydrochloric acid with magnesium, is the one that we saw in the lab, in which we had the eudiometer to measure the amount of hydrogen gas coming off. And so hydrogen gas is a product of the single replacement reaction, in which we're going to make MgCl2, the 2 because magnesium is a +2 charge, and that's an aqueous salt, and we're going to make hydrogen gas. And we've already got the 2 in front there to balance it, so I don't need to do any balancing. And many different metals will undergo this reaction. A few won't. Copper won't do it, for instance, and silver and gold won't, but most metals will do this. Another thing is you can react with either carbonate or hydrogen carbonate, and when you do, the carbonate comes out and forms carbon dioxide. And this is the basic baking soda and vinegar experiment that you may have done back in elementary school. Acetic acid is vinegar, and it has an H here, and we'll talk about that later on. Baking soda is a base, and it's got this guy, and how it works as a base we'll talk about in tomorrow's lesson. But essentially what's going to go on here is this is very similar to a double replacement reaction. The sodium and the acetate, the C2H3O2, are going to come together to form a salt. And then what's going to be left over is H2CO3, but that H2CO3 actually decomposes right away into H2O, and there's a carbon dioxide gas that we're looking for, and this is what gives that volcano its fizz. Acids taste sour. In fact, the word vinegar comes from, I'm going to slaughter the French, so please excuse me if you speak French. Vinaigre, vinegar, sour wine, and vinegar was first found in wine that had gone bad. So sour wine is vinegar. So if you remember that, you'll remember sour tastes. Lemons, remember lemons taste sour. And tangy. So you might also get a tangy taste out of something that's acidic as well. They will turn blue litmus paper. So you're going to take blue litmus paper and turn it red. Now, I usually do a demo along with this because it kind of emphasizes what's going on. I'm trying to find some good YouTube videos to go along. If I find some good YouTube videos, I will post them along with the notes. Now, remember, acids are dangerous. How do you remember the red? Acids are dangerous. And what's the big danger color? Red is the big danger color. And so we remember acids are dangerous, gives us red, and we can think of them as hot. They'll give us those chemical burns. And they do feel like actual burns, but they're not the same as heat burns. Another important property of acids and bases, we'll get to bases in a moment, but acids especially, is that they are electrolytes. And we saw this back in chapter 8. If you remember, an electrolyte was something that conducted electricity in solution. That's because acids are going to make ions. And we'll talk about how acids make ions in a few minutes. Strong acids make strong electrolytes. Weak acids make weak electrolytes. And we will see, if I find a video, hopefully they'll have something showing you the differences in the strengths of electrolytes. So that's our look at acids. I haven't talked about pH paper in here because we really haven't talked about pH yet. We will talk about pH in a few lessons, but pH paper can tell you pretty much where this falls in the acid spectrum. Bases are kind of the opposite of acids, but they don't have all the opposite properties. Bases are corrosive to skin, and skin, we sometimes call that like tissue. Not like Kleenex tissues, but skin tissue, but not to metals. Most metals don't have any reaction with bases. There is one, but it's not important to us. Bases taste bitter. So bases are bitter. There's a B and a B going together to help you with that. If you think of green leafy plants, things like broccoli rabe or kale, these are what are called alkaloid plants. And bases are called, there's another word for bases, are called alkalis. And so that is another word for base. Yes, it's the same alkali as alkali metals, and we'll see these in a few minutes. Bases also feel slippery, like soap. And in fact, you do use bases to make soap. Bases are going to turn red litmus paper blue. And so it's the opposite. In that respect, it is the opposite. Where's my red litmus paper blue? It is the opposite. That doesn't look like a blue. B-L-U-E. And B for blue, B for base. So you can use red litmus paper to test for the presence of a base. Bases are also electrolytes because when they dissolve, they form those mobile ions that we need to make electrolytes. And as before, strong goes with strong. So strong bases are strong electrolytes, and weak goes with weak. Finally, there's something called phenolphthalein. This is an indicator. Now, acids and bases all react with indicators, but phenolphthalein is an important indicator. We're actually going to see this later on in our pseudo lab. Phenolphthalein is an indicator, and bases turn phenolphthalein pink. It's actually a magenta color, and it's kind of pretty to see. The bad thing is that the stronger the magenta color, the worse your experiment is, and I'll talk about that when we introduce the experiment next in a couple of lessons from now. So these are some typical properties of acids and bases. Now, acids and bases work because water itself has some chemistry. And we'll come back to this when we talk about pH, because that's really where this water chemistry and where pH comes from. But it turns out that in water, if you take the concentration, remember these brackets mean concentration, the concentration of hydrogen ion, which is an acid, so this would be an acid, and hydroxide ion, which is a base, is constant. So it's constant. So as the hydrogen ion goes up, that means that the hydroxide ion concentration has to go down. And if you remember from all the times we have two things that are multiplied together, this is an inverse or an indirect relationship. As one goes up, the other has to go down. And so this is what gives water a lot of its acid-base properties. In water, you'll have an acidic property or acidic solution if the hydrogen ion concentration is greater than hydroxide. The only place where it's neutral is where the two concentrations are equal. And again, when we talk about pH, we'll see how that works. And in a basic solution, it turns out that the hydroxide concentration is greater than the hydrogen ion concentration. Oh, and pHs, and we'll get to pHs later. For an acidic solution, pH is less than 7. For a neutral solution, pH is equal to 7. And for a basic solution, pH is going to be greater than 7. And again, you'll see why that works when we get to pH. So let's finish up today's lesson by looking at the first model for acids and bases. And this is called the Arrhenius model. And in the Arrhenius model of acids and bases, acids ionize in water. So you put them in water, they ionize, and they're going to form H+. Now, H+ is how we sometimes abbreviate it, and I did so just above. But that's not how it really exists in solution, and often it's written as H3O+. H3O with a positive charge is really H2O plus an H+. So if you look at it, you'll see the H2O and the H+ in there. That has a special name that we're going to be referring to in this unit. It's called hydronium, the hydronium ion. HCl. Do you remember the name for HCl? HCl, hydrochloric, hydrochloric acid. That's the acid that's in stomachs. You can also buy it in the hardware store as muriatic acid, and you can use it to clean concrete. If you do so, make sure you have some very good personal protective equipment, not only a dust mask, but you need to have actually a filter that filters out the hydrochloric acid fumes, and goggles and gloves and long pants and all the works, because it's 12 molar, very concentrated, and so it can be very dangerous to use. In water, what's going to happen is the hydrochloric acid is going to decompose, or it's going to ionize to form H+ and Cl-, and there's the ions that we had before to make this conduct electricity. And this is a strong acid because the ionization is 100%. Ionization. So strong acids ionize 100%. In other words, every HCl splits apart to make an H+ and a Cl-. This next guy, do you remember the name of this guy? It's got sulfate in it, and there's an O, so it's no hydro, and so we take sulfate and we make sulfuric out of it. Sulfuric acid. This is what you find in car batteries, and it can be dangerous in car batteries if you're not careful, because, as I said, acids will react to form hydrogen, and if you go to jump start a car and you make a spark, I don't think this happens as much in modern batteries, but in old batteries you had to be careful because there could have been hydrogen gas present, and the spark will ignite the hydrogen gas, make the battery explode. And years ago, many people suffered acid burns when they tried to jumpstart a battery. With sulfuric acid, it turns out that only one of the hydrogens comes off the H2SO4, and so when we put that in water, by the way, the water over the arrow can indicate, in this case, the way I'm indicating it, it's not necessarily taking place in the reaction. It will, and we'll see how that reaction works in the next lesson when we see how water gets involved in this. But we're going to make a hydrogen ion. That's aqueous. And when you do that, you take off the hydrogen ion, and we're going to make HSO4- as the ion that's left over. Again, strong acid, that goes 100%. Not all acids do. We'll talk about one in a few moments. Finally, this last guy, by the way, we have those H's in front. So that H, that's how you tell you've got an acid. We have the H. We have that H in front. That's how you tell you have an acid, if you remember correctly. HNO3, we've got nitrate. Adic-itis tells us that's nitric acid. And nitric acid is commercially very important. It's used in synthesis of fertilizers. It's used to make ammonia, which has nitrogen in it. And as before, take the H2O over there, and we're going to make H+. And it should be a Q. Let me rewrite that as a Q. And NO3- nitrate is also aqueous. And again, a strong acid, so it dissociates 100%. Now, there are only 6 strong acids, and we'll talk a little bit about them over the next couple of days. These are 3 of the 6, and we'll get to some of the others later. Don't worry about them. I will tell you if you get a strong acid or a strong base. This last guy, this is acetic acid. And we either have put the H in front. I'm not sure why I didn't highlight it in yellow. Looks like I did on the notes. I'm not sure why that didn't come across. And so we can write it as HC2H3O2, or we can write it as CH3COOH. Now, if you see the H in front like that, or if you see the H at the end of a COOH, that's what tells you you've got an acid. And these are what are called organic acids. So this happens to be acetic acid. It came from the acetate anion. And because of this, the acetic acid, it's a weak acid. What does this weak acid mean? Much, much less than 100% ionization. And in fact, acetic acid has about 1% ionization. So it's a very weak acid. Few ions in a solution, and so this is a weak electrolyte. It won't conduct electricity very well because it doesn't have a lot of ions in solution. Now, acetic acid and that COOH is important. To be an acid, the acetic acid must come from a relatively weak, a weaker, more polar bond. In which the H is attached to a very electronegative atom. So to be acidic, we have to be attached to something like chloride. Now, this is a weak bond. This is polar. There's a delta plus and a delta minus. Sorry, that would be the delta minus. Delta plus and a delta minus. But this happens to be a weak bond, and that's what makes this strong acid. The weaker the bond, a weaker bond gives you a stronger acid because it's easier to pull that hydrogen off. And the easier it is to pull that hydrogen off, the stronger the acid's going to be. In oxyacids, the acidic hydrogen, now when we write HNO3, it looks like we're putting the H on the nitrogen, but that's not where it actually is. The H is actually attached. It's bonded to an oxygen. This is going to be true of all these oxyacids. Now here we have a delta plus, we have a delta minus, we have a delta plus here, and delta minuses here and here. And what happens in this acid is it turns out that because of the negative and positive here, this pulls electrons off, it pulls electrons away from the hydrogen. And what that does is it makes it more polar. And making it more polar is what makes it a strong acid. The more polar it is, the stronger the acid you have. In acetic acid, we have something very similar. Now, in acetic acid, we also have something else to worry about. In acetic acid, oh, by the way, let's show that bond there, that OH bond is what's going to split, and that hydrogen comes off. In acetic acid, we have the delta plus on the hydrogen, we have the delta minus on that oxygen, a delta plus and a delta minus. In acetic acid, we have that pulling away of the electrons, but it's not as strong. It's a weaker pulling. And so it's a weaker acid. But again, this hydrogen is the one that's going to come off because it's attached to that oxygen, and we'd split right there. Now you might say, what about those other hydrogens down the line? What about these hydrogens? If you remember way back in our polarity lab, we started drawing delta pluses and delta minuses on these structures. And remember, there's no delta plus or delta minus because the carbon-hydrogen bond is non-polar. So these hydrogens are not acidic hydrogens. And that's why we can write them differently. If you look up above here, That's why we have that CH3 like that. That CH3 is telling us that those 3 hydrogens are not acidic, and only the hydrogen at the end of the COOH is going to be acidic. So anytime you see something that has COOH, you know it's acidic. Or here, those 3 hydrogens here, those are the 3 hydrogens that are not acidic. And in any formula you see, if there's an H out in front, that's the acidic hydrogen, or hydrogens. There can be more than one. Any hydrogens that are attached to a carbon are going to be in the middle of the formula like that, and those are not going to be acidic hydrogens. So those are acids. Bases. The Arrhenius model of bases tells us that bases ionize to form hydroxide in solution, and especially metal hydroxides such as sodium hydroxide are considered bases. They are metal hydroxides. They're actually ionic, and so they'll split at the sodium and the hydroxide. And sodium hydroxide is a major ingredient in lye and Drano, which help clean up clogs in a sink. Hair remover, if you ever use any of those chemical depilatories like Nair or Neat, I don't know if those both exist anymore. I think one of them does. You're actually putting some sodium hydroxide onto your skin. And if you're not careful, I think they tell you to be very careful, that you could actually get chemical burns from it. So again, in water, we're going to take the sodium hydroxide, just like any ionic compound, just like sodium chloride would. We're going to take that sodium hydroxide, we're going to split it apart into sodium ions that are aqueous and hydroxide ions that are also aqueous. And there's our ions that make this into an electrolyte. This is a strong base, and as with strong acids, strong base also dissociates or ionizes 100%. Ionization. MgOH2, magnesium hydroxide. So the hydroxides of the alkaline earth metal. So we get the alkaline metals there, and there's that word alkali again. And the alkaline earth metals. Let me spell it right. Alkaline earth metals. Those are going to be bases as well, or any metal with a hydroxide. These are just the stronger bases. This is sometimes called milk of magnesia, magnesia from magnesium. And it's used as an antacid because it will react with and neutralize acids. And in a couple of lessons, we'll talk about neutralization equation, neutralization reactions, and see how those work. So magnesium hydroxide, again, it will split here. The only thing you've got to be careful of is some stoichiometry here. We've got 2 hydroxides there. So when we split that apart, it's going to make magnesium. Now, magnesium ion, remember, is a 2+ ion. And you can see that that's why we need the 2 hydroxides. That's aqueous. And 2 OH minuses, aqueous, to round us out. Now, there are some compounds that look like they could be bases. Something like this guy. This is methanol. Sorry, Ethan, I didn't use ethanol in this case. Methanol, which is also sometimes called methyl alcohol. This is the bad alcohol. This will make you go blind if you drink it. So don't drink this stuff. You shouldn't be drinking any alcohol, but don't drink this stuff especially. Now, it looks like it might be able to split at the CH3 and the OH. The problem is we've got this CO bond. The CO bond is covalent. This is a molecular compound, which means it's all covalent bonds. And even though we've got this hydrogen here, and yes, this is a delta plus and a delta minus, and there's a delta plus here, what's going on here is there's not enough pulling. There's no pulling, so it's not an acid. And the covalent CO bond means that unlike up above where we had the bond, it was ionic bond, the covalent CO bond does not break. And so this is neither an acid nor a base. Okay? And we will talk about that. We'll see that in our notes. All right. That's our introduction to acids and bases. I think you'll find that the homework is based pretty much on what we just talked about here. So go ahead and do that homework, and we will see you next time in class.